Earlier in the year, we learned about how power plants generate electricity, and we focused on it in terms of energy transformations. We're going to revisit generating electricity, but this time we're going to look at it in terms of chemistry. Just as a refresher, power plants are structures that generate electricity. They start with some sort of natural resource, for example, natural gas, coal, or uranium, and they go through different processes to generate electricity. The super important part of a power plant is the generator. And in our energy unit, we talked about how generators just transform one form of energy into another. They transform kinetic energy from the rotating, moving wire in between these big magnets into electrical energy. We can see this happening because all of these little bright dots, remember, represent electrons in this wire. And wires are great conductors because they allow these electrons to flow so easily. And as you rotate this wire within the magnetic field, it forces those atoms to start moving. You can think of it almost as like pressure in a pipe forcing water to start moving, like when you open a sink. And so that current gets going, and that current of moving electrons is electricity. So generators, kind of a misnomer, because they don't really generate or create energy, because we know, because of the law of conservation of energy, that that's impossible. They really transform moving kinetic energy into electrical energy. So the basic steps of generating electricity. First off, in power plants, you need to boil some water, and you do that in order to get steam. You need the steam because that pressurized gas is going to get moving really fast and spin huge metal turbines, 2,000 rotations per minute, so moving really, really fast. And those turbines, in the end here, are connected to a generator. And the faster you spin that generator, the more electricity you're going to get out of it. So here is just an image of steam coming into the generator. It passes over the turbines, and since they have those blades, just like a fan in your classroom or your house, those start spinning. They're connected to this shaft, which attaches to our generator, which gets those wires spinning, and they're surrounded by magnets. There's our electricity coming out the end. So that was a review on energy transformations, but now some new stuff. So if we just start off with coal, where does the energy actually come from that we're transforming? Let's take a look at that. So in a coal plant, you'll remember, in order to boil that water, we saw that they pulverized the coal, they broke it down into really small pieces, and then they lit it on fire. All that burning something is really taking something, giving it a little bit of energy, like maybe a spark, and letting it combine with oxygen. And as coal and oxygen combine, they produce carbon dioxide. And just producing that carbon dioxide, mashing these two things together, bonding them together, you release a ton of energy. And I'm showing fire here just to represent all the energy that's released. Coal is really just carbon, oxygen, O2. When you combine those together, CO2, carbon dioxide. Reactions that release more energy than is put in are called exothermic reactions. So when we're talking about power plants, if we want them to generate heat, we need whatever reaction in them to be exothermic. Nuclear power plants work very similarly in that they have to heat up water, create the steam in order to turn the turbine in the generator, but they come at it from a really different way. Instead of combining two atoms by burning something, they break atoms apart. Uranium is a really famous atom. It's been used in weapons, but it's also used in nuclear power plants. It's a very large and unstable atom. And in a power plant, when they shoot a neutron at uranium, it actually causes the thing to break apart in this process called fission. When uranium breaks apart like that, it releases a huge amount of energy. And then, since you can't destroy matter, now the smaller pieces of uranium are actually themselves just smaller atoms. There are many different combinations that uranium can break into, but one would be barium and krypton. So just like before, we noticed that there is more energy released than it took to get fission going. So this also is an exothermic reaction. So different power plants start off with different natural materials. Coal, oil, natural gas, uranium, they all might look and behave very, very differently. But what's important is that they can all undergo exothermic reactions, which means that they release a lot of energy that we can use to heat water to generate electricity. Even though these are great sources of electricity, coal, petroleum, and natural gas are what's known as non-renewable resources. And nuclear power, it's kind of in between. In order to get natural resources like oil or natural gas or coal, it takes organic material that dies and sinks to the bottom of the ocean or a shallow sea millions and millions of years ago. After millions and millions of years of intense heat and pressure, they actually go through a transformation, becoming oil, natural gas, and coal. We call these materials non-renewable because it takes millions of years for them to form, and we use it up much quicker than it actually forms. In fact, we pump about 80 million barrels of oil out of the ground every single day. To put that in a measurement that we're more familiar with, that's over 3 billion gallons of oil every single day. So that's why we call it non-renewable. We cannot renew the amount that we have fast enough to keep up with the demand that we have for it. Renewable resources, on the other hand, are any sort of resource that we actually don't use up faster than it's made. They can replenish themselves at a faster rate than we can use them up. Examples of renewable energy sources are solar, wind, and kind of nuclear power. Technically speaking, nuclear power is really, really abundant because it's in all the nuclei of all the atoms in the universe. But the specific type of uranium that we use is very, very rare. So as it is right now, technically nuclear power is non-renewable. So let's look at the chemistry of some of these renewable resources. In solar panels, you have a layer of silicon. So if we were to zoom in, we would see these atoms of silicon right here. When sunlight hits a solar panel, the energy in the sun's rays actually knock individual electrons off of the silicon atoms. Those electrons are now free to flow through electrical wires. Each of these little circles would represent the silicon atoms, and these purple dots with negatives represent the electrons. These flowing electrons are electricity. Wind power is more closely related to how we saw non-renewable resources generate electricity. Except instead of burning something to generate heat to create steam to turn the turbine, this one just uses wind to turn a massive turbine that's out in the open. That turbine is directly connected to a generator, turning that kinetic energy into electric current. So no matter if you're using non-renewable resources like natural gas, oil, coal, or renewable resources like solar and wind, or something that's in between, the whole purpose is still to get electrons flowing.